weak acid equilibria is our topic for the day. So if you open it up, hopefully you can access the slides and all that stuff, all that jazz. So I've got recommended SciPad problems and EP. You choose one or the other. Remember, don't do both because you're overworking yourself. But if you do one or the other, you should be adequately prepared. So let's get into it. Weak acids. So there's some vocabulary we need to know. Here's the vocabulary. You might have recalled that I mentioned maybe at level 2 something called Bronsted-Lowry. The names aren't as important. Yep.
It's not on the screen.
It's not on the screen. Why isn't it?
Oh no.
I'm just talking to myself now. So now that it's back up on the screen, you can actually see what I'm talking about. So we've got the vocabulary for the first half of the class. Before we get into the calculations, we need to talk about concepts such as Bronsted-Lowry acids and bases, amphiprotic substances, conjugate acid-base pairs. That's familiar, right? Yeah, cool. Amphiprotic, is that familiar to you guys? Cool. We'll go over the definitions. Strong versus weak acids and bases, of course, that's a big level 2 topic, you know that. And something new called the acid dissociation constant, or K sub A. Kind of similar to K sub S, but that's for solubility. This is for weak acids that partially dissociate. And they are in equilibrium. Cool. So we'll go through each of these topics one at a time before we hit Ka and get into writing expressions for that acid dissociation and doing some calculations. Just give me a second. I see some people jotting things down already. My 7 Chem class really enjoyed my chemistry pun on the window, by the way. And by enjoyed it, they thought it was really bad. But
That's a level of enjoyment.
okay, so the first topic in that vocabulary list was Bronsted-Lowry acids and bases. And that's just the name of the concept or the definition of acids and bases we learned last year, that acids are proton donors, bases are proton acceptors. That's literally it. You know this already. You may not have called it Bronsted-Lowry, but that's the names associated with this definition. There are other definitions of acids and bases besides these. Not all acids and bases are proton donors or acceptors. They do other things with lone pairs of electrons. And so you can be acidic but not actually donate protons. It's kind of cool.
I could be an acid.
You can be anything you want to be except maybe an acid. I don't know. So in water, H plus ions exist, we know, as hydronium. That's something we learned last year. At level 1 science, we just said H plus ions, but they really react with water to form hydronium, H3O plus, right? And so we know in this example, for instance, we see HCl acting as an acid because it's donated a proton, and for everything that's acting as an acid, there must be something acting as a base. And water, even though it has a pH of 7, is acting as a base. It's accepting a proton. By definition, that makes it a base. Now over on the right side, we have water doing the opposite. Water is donating a proton to ammonia. So in this case, water, once again with the pH of 7, can act as an acid or a base. In this case, it's acting as an acid. And ammonia, we know, is a base because it's accepting that proton to form NH4+, the ammonium ion. Cool. So water can do both things. So this links with our next topic. If water can do both things, if it can be both a proton donor, an acceptor, an acid, or a base, what do we call that?
Amphiprotic.
Amphiprotic, yeah. What were you going to say, Ella?
Does that kind of link into what you're saying about like water as a just straight water? Like you had to take water into the equilibrium between like H3O plus and OH minus.
That's true, yeah, because that happens because 2 water molecules are reacting with themselves, right? 2 water molecules, and one of those water molecules is donating a hydrogen and the other is accepting. So they're both waters, but one's doing one job, one's doing the other.
That's like always happening in like second bowl of water.
Yeah, yeah. So it does contain mostly water. Remember, it's an equilibrium, and there's far more reactants than products. And that's reflected by the Kw value, the Kw constant for that reaction, right? So in that equation, we know that Kw is equal to what number?
1 + 2 to the negative 2.
Yeah, which tells you equilibrium lies very far to the reactant side because it's a very small number. And I'll just write out that equation again in case some of us are trying to visualize what's going on. 2 water molecules react with one another one donates a proton, one accepts a proton, and we get a hydronium ion and a hydroxide ion as a result. So one's donating, one's accepting. That's a great demonstration of the amphiprotic properties of water reacting with itself. Well, not itself, but another molecule that's the same. Cool. Great link, Ella. That's awesome. Okay. Amphiprotic substances. We don't need to spend too much time on this. It's, you know what it is. It can donate and accept a proton. But here's some other examples down here. So hydrogen carbonate's a great one, right? You know, for regulating things like ocean pH, right? Because it can accept a proton to form carbonic acid, H2CO3, or it can donate a proton and it can become the carbonate ion, CO3 2-. We have the hydrogen sulfate ion, which can be plain old sulfate, SO4 2- if it donates a hydrogen, or it could accept one more to form sulfuric acid, H2SO4. And we have dihydrogen phosphate. So it can accept a proton to form phosphoric acid, or it can lose one as well. So anything with one hydrogen that can accept one more will often be able to lose that one, so that makes it amphiprotic. All cool? Cool. So you know this stuff. Just write down what's important because you know most of this stuff. Let's see if we can fill this example in though. This is from a level 3 exam from 2 years ago, the 2018 exam. So the hydrogen sulfate ion is amphiprotic. Can we complete these two equations to show it acting as an acid, acting as a base? Real quick, can we predict those products? Johnny, think you got it? Have a look. Yeah, acid on the top.
I'm assuming you want us to balance them as well.
Yep, but there shouldn't be too much balancing to do. Okay, I think we're good. So if it's acting as an acid, it's losing one, so we should form the sulfate ion. As a base in the bottom row of the table, it is gaining one to form sulfuric acid. Sweet. Cool. Last thing, one of the last little terms we got to review are conjugate acid and base pairs. So this should be familiar, I think, for most of us from level 2. The idea that these pairs differ by a single proton because one has donated it. And so we can see that the arrows show the pair. So in this unit, we're going to become familiar with the general formula HA representing the formula for a weak acid. H standing for that proton that the weak acid is potentially able to donate because it partially dissociates, and the A standing for the rest of the acid's formula. So after it potentially dissociates and releases some of those H ions, then its conjugate base is represented by the symbol A-, right? So if we were to look at ethanoic acid as a common example, and hey, that's what we got here. Ethanoic acid has the formula CH3COOH. And when it loses a hydrogen, it becomes the ethanoate ion. It's lost that hydrogen from the carboxylic acid functional group. So it's the ethanoate ion. We represent it with the generic symbol A-. And the base is water. It's a solution of a weak acid molecule in water, and the weak acid, or ethanoic acid, gives the hydrogen ion to the water to form that hydronium. Remember, the hydronium is what makes it an acid. The presence of that makes it acidic. So we have our conjugate acid-base pairs that differ by a single proton. And in this case, we have two pairs. Water and the hydronium is one pair, and the ethanoic acid and the ethanoate is the other one. And the arrow underneath the reaction just shows the transfer of hydrogen, where it's going to. Cool. So we know that. The other symbols we need to get familiar with are that B, surprise, surprise, stands for base. Who would have thought? If A.
If I had to guess, I would
Yeah.
know that.
And when it accepts a hydrogen, we write the formula BH plus. So the base with that H plus ion that it's accepted. Okay? These symbols will come up from time to time over the next couple weeks.
Could you make it up just?
So here I've got ammonia.
Do they ever distinguish the base symbol for B to like? Do they differentiate anyway? So you
From
don't
boron?
know boron.
I saw you looking at the table. No, they don't. We just don't talk about boron in this unit.
Boron's not a thing.
Yeah.
Don't worry.
Okay.
Yeah.
Boron doesn't exist. Got it.
That's a really good question. What happens when you have an acid involving boron and or a base or something? Yeah. Okay.
Tin doesn't exist.
Yeah.
Just a second.
But borons never react with an acid.
I've got it here, Emma.
Oh, thank you.
It's cool because it's fine having like 3 bonds and 6 electrons instead of an octet, you know? BF3. It's a prime example of a trigonal planar shape. Banana bond? What? Banana bonds. Dude,
I still love the fact that radioactivity is measured in bananas.
Yeah.
You
Yeah.
can measure it.
Okay. Let's move on.
Wait, like if I eat a banana,
Now,
that's quite a lot of radiation.
with these next 2 slides, you probably don't need to write much down at all. Just absorb what's there. You know it. Don't write down things you already know and spend too much time on things you do know. So, strong acids, you know, completely dissociate. Weak acids partially dissociate. That's the point. We know that, right? That's the difference between strong and weak acids, right? Cool. Moving on. What about strong and weak bases? Strong bases are compounds where every molecule accepts a hydrogen ion. And weak bases are a compound where only some molecules will accept an H plus ion. Yeah,
Just to double check, when you're writing the equation for the weak ones, it's equilibrium.
always, yes.
Because it
Good
partially
point.
dissociates.
Partially happens, yeah.
Yeah, right.
Cool, yeah. You've noticed that, yeah, good. So if I ever put a forward arrow on anything in this unit, really, say, why'd you do that? Yeah, yeah, cool. Cool. Now this might be new to you. This kind of makes sense though. Let's link what we just learned about weak and strong acids and conjugate acid-base pairs. So the stronger an acid, the weaker its conjugate base is. So if we look at a strong acid, and the strong acids are all near the bottom of this list. So we have HBr, sulfuric acid, hydrochloric acid near the bottom in red here, right? These are strong acids. Their conjugate base is really weak. Why? Because anytime you're trying to give a hydrogen ion to a chloride ion, it'd be like, no, go away. Because that's what hydrochloric acid does. It dissociates completely. It gets rid of its H ions, right? So if you were trying to make these chloride ions accept a hydrogen and act as a base, it'd be like, no way, because as soon as I have a hydrogen ion, I become HCl again. And what does HCl do? It gives it away immediately. So the stronger the acid is, the weaker the conjugate base is. And vice versa. If a base is really good at accepting a hydrogen ion, then its conjugate acid form will be really weak. Cool? So it's not just a rule, but it makes sense, right?
Wait, walk me over the opposite. So I get the one with the Cl, but the other way around?
So if you had a strong base, like O2 minus is at the top of the list right there. It's really good at accepting hydrogen ions. So it'll form something, it'll form the OH minus there. But we know OH minus is the conjugate acid of O2 minus. It's kind of weird to think of hydroxide as the conjugate acid of something, right? But that makes sense. It's weird to think that, and that's normal to think it's weird because we know hydroxide isn't going to donate its one hydrogen anytime soon. At most, it's going to it's going to act as a base and maybe accept another hydrogen ion to form water. So O2 minus is a strong base, and its conjugate acid, hydroxide, is weak for that reason. Because if the strong base really wants to accept a hydrogen, its acid won't want to be a strong acid because it'll still have the potential to, I guess, accept. Cool? Makes sense? A bit? Ella's kind of, no. the acid example made sense, right?
Yeah. About the HCl just being like, no, go away.
Yeah, yeah. Because if you're trying to give an acid or a hydrogen to the chloride, it would say no, go away. Yeah.
So which one's saying no, go away out of the acid or base in the other level?
So you know the base is strong, it wants to accept a hydrogen, and when it does, it forms OH minus. Now, OH minus, we know is actually alkaline. It's a base, meaning it's going to be weakly acidic. It won't have the potential to donate that hydrogen. It'll still want to accept another one rather than give away one.
Oh, yeah, right.
Yeah.
Okay, yeah.
Cool.
It's a terrible acid.
Yeah, it's hydroxide is a terrible acid.
No, right now I get it.
Lesson of the day. Cool. So putting it all together, just some basic knowledge we had, you know, if we use red litmus paper versus blue, we know what colors it should stay or turn into. So red litmus paper stays red in acidic conditions, and it turns blue in alkaline, and vice versa. And at pH 7, they both stay red or they both stay blue. And we know the relative concentrations of hydrogen to hydroxide ions at the different pHs. That's just stuff we know. And these are all equations we worked with over the last couple lessons, right? We've been thinking about these quite a lot. We bring them up on the screen every time you asked, oh, I forgot that equation, what is it again? Because it is provided on the resource sheet in the exam, so we should have them in front of us. You don't need to memorize these. It's good to be familiar with them a little bit. And how to rearrange them. So especially this one here for the water dissociation constant. When you rearrange it, can you visualize that these are the forms that you get when you rearrange this central one? Because they give you this central equation, but I don't believe they give you the rearranged forms, so you have to do that yourself. Cool. Awesome. Sweet.
Zach,
Yeah.
is OH minus amphiprotic? Because it can both donate and accept hydrogen?
Yes, that would make sense.
Okay.
But it does one more than the other. We know. Yeah.
Would make sense.
Yeah.
Thank you.
Yeah. We know it's going to accept a proton more than it is going to donate one, because it is a very, very weak acid, as we just talked about. It's a very, very weak compared to the O2 minus. So cool. Good question. Is OH minus amphiprotic? I didn't have that on my list. I guess it technically is. Okay, and this brings us to our first brand new topic, and this is the main focus of today. Today's focus is weak acids. So this is the big thing today, the acidity constant, or the acid dissociation constant, I prefer to call it. Pretty self-explanatory. Weak acids partially dissociate. Hey, we can write a constant for that equilibrium, just like we did for solubility. Once again, representing concentrations of products over reactants in our equilibrium expression. So our products are the conjugate the conjugate base of that weak acid, and that's represented by the symbol A minus. So A minus is the conjugate base of that weak acid after it's lost its acidic proton. And hydronium is obviously produced because it is an acid. And that's divided by the concentration of our reactants. We don't include water, we know that, but we do include the weak acid, of course.
And then just read it and I was like, oh.
Okay.
She looks so disappointed.
So now that we've got the equilibrium expression for a general weak acid reacting with water, forming its conjugate base and some hydronium, and we've got this expression, you know, we can do all the same sort of maths we did last time, so it's routine. There's not a whole lot of new stuff today, just the idea that we can apply what we applied to solubility to weak acids, and we can do all the similar calculations associated with it. And you're like, sweet, that's cool. As we get into this over the next week or two, we're going to get into new topics like buffers. That's really interesting and has a lot of good real world context. So like regulating blood pH, so we don't die when we drink orange juice or anything acidic. That's important.
Ocean pH.
And ocean pH, yeah. So a few other contexts as well.
The blood one's probably the most interesting though, I would say.
And I think we were talking about that the other day. You know, those misleading advertisements for like water and stuff where they said the pH is just right so you doesn't throw your blood pH off balance or anything like that, you know.
Your blood doesn't anyway, so it doesn't matter, you're just selling more expensive water.
Yeah.
If you drink
Actually,
enough
their
juice,
water is more
it will
likely
overrun.
to go.
If you
Drink
drink
enough, because
If
it
it's
will
just
go
added
if you drink
or
or if you eat enough bananas, you'll die from radiation poisoning, but that amount is like millions and millions and
That's
impossible
why I
to eat in a
was
certain
like,
time.
Yeah, you die from
If for some
calcium.
reason
You die from yeah. Yeah. Okay.
drinking
Um,
it would be terrible.
You know, what if you are not in a room with those bananas?
Like,
Nelly, disproving science.
It's
It's not science.
Tell me about the acidity constant, Zach.
Thank you for getting us back on track, Ben.
Thank you, Ben. Oh, I tried.
Ben really wants to hear about the acidity constant, guys. Basically, it's the same thing as we know about regular equilibrium constants. Basically, the smaller the value is, the more equilibrium lies towards the reactants. The larger the value is, the more it shifts towards the product, forming more products relative to reactants. Because remember, that constant is a ratio of products over reactants. If you have a large numerator, you're going to get a large number. So typically, in this unit, because we're looking at weak acids, our Ka value is going to be much smaller than 10 to the negative 3. So we're focusing on this case on the left here, really. And anything that's strong or strong acid will have a large equilibrium constant. Well, not even an equilibrium constant. Basically, it's formed entirely products. So this is just refreshing us on what this magnitude of K means. I think we know this for the most part. If it's exactly 1, that means we have an equal concentration of products to reactants. That ratio is 1 to 1. But that's usually very unlikely.
Is there anything you know off the top of your head that?
The form's 1 to 1?
Yeah.
No.
No.
If you find one, that'd be awesome. It's like perfectly balanced. It'd be a Thanos situation. Thanoic acid. That's what I'll call it.
The kind of rumbling.
Are you hearing music in your head again?
you okay? It is, I swear it's real.
No, you can hear the piano room all the time from here. It's very faint, and it's like, oh, that's cool. Cool.
No, I don't have anything today.
Let's move on. So thanoic acid, it's now a thing. I've called it that. And we will find it, what it is.
We will find it.
We will
And
find
if
it.
it's not purple,
Like
it's
one
the
Higgs
wrong
boson.
thing.
When put an indicator, it should go.
Couple important equations that are probably new to us, but
Universal indicator.
analogous to what we know about pH. You know how the pH is equal to the negative log of the hydrogen or the hydronium concentration. Yeah, that's an equation we know. Analogous to that is an equation called the pKa, and that's equal to the negative log of the Ka. Ooh. Ooh. That's you're like, why do we do this? Why do we just make up random equations just
Why
to
we
do
here?
things? Yeah. It's because, you know, the Ka is often a weird value, like maybe 6 times 10 to the negative, like 12. Okay, that could be the Ka associated with some weak acid. That's not a great number to discuss in conversations if you have to say this long string of words to explain a constant associated with something. So what we do is we convert it to a nice form. Did somebody calculate the negative log of 6 times 10 to the negative 12?
No, my calculator is not turning on.
Oh,
That's
okay,
a bit
never mind.
okay.
You cannot fill out what you said you would.
You got this.
10 to the
Negative 12.
11.22.
So I'll round it to 11.2. So much like pH gives us a nice number to talk about between like 1 and 14, pKa gives us a nice number we can talk about. And it means something. So the higher the pKa, the weaker the acid. Because the Ka is very small, right? That means it dissociates very little. So much like how the higher pH means it's a weaker acid, right? Like if the pH was 12, you'd say, oh, that's not even acidic at all, right? analogous to that, the pKa tells us something about the characteristics of how much the acid dissociates. So a high value of pKa means it's a very weak acid. If the pKa was closer to like 2 or 3, it'd be a stronger weak acid, you know, that sort of thing.
So weak
Cool.
acid that he's trying to work out.
Yeah. So typically for a weak acid, as this table says, the pKa is somewhere between 3 and 5 for a weak acid. Cool. The pKa we just calculated is more in the range of a very weak acid. So the higher the pKa, the weaker the acid. But a very weak acid with a high pKa has a very small Ka, so they're inverse of one another, right? Very small Ka means a very big pKa. That's the point of this. So the pKa is a nice number to talk about. And often in questions that you'll see on the exam, the question will say the pKa for this acid is this number. And they do that because it's nice to talk about and state. But in our calculations, because we know the Ka expressions often start with Ka being equal to some products over reactants, this is Ka, not pKa. What we're going to have to do as a first step in all of our calculations is convert the pKa given in the question to a Ka value to do the rest of the steps. So can we do that? Yeah. Look, that's where the second equation comes in. So Ka is equal to 10 to the negative pKa. Does that seem similar to an equation we know from level 2? Acid and bases, yeah. When we're trying to find hydronium, because hydronium is equal to 10 to the negative pH. So this is kind of analogous to that. So this equation here, and in the box on the screen, is what we're going to often have to use in our first step of every problem we solve.
So the pKa we got was 11.2.
Mhm.
And what is it usually between?
For most weak acids, between 3 and 5.
That's 11.2.
It's just a
So
random
it's a
number.
very,
They're very,
weak
very
acid.
weak acids. But like average weak acids, you know. Weak acids have different strengths. Some dissociate more than others.
Is there a basic constant?
Hey, yes, there is.
Oh.
There is something called K sub B for bases.
But we talk about it less.
Talk about it less.
Yeah.
It's like the,
Case of boron.
yeah, I won't say. That's good.
The boron
It's a boron of a.
boron constant, yeah.
Okay. Okay.
The chemistry group.
So let's do some calculations of Ka and pKa, applying these calculations and these equations to the following pages from SciPad. Just 1 and 3. Skip number 2 on both of these. Page 272, 1 and 3. Page 273, 1 and 3. Hydronium concentrations are equal to the conjugate base. And I was saying to Ben that this is pretty much a valid assumption, but it's not technically true. It's not technically true that the concentrations of these two species are equal. Can somebody else maybe think up what the explanation is who didn't overhear that conversation? Which of these two ions, the hydronium or the A-, do you think is actually in higher concentrations at equilibrium? And why? Annabelle.
H3O plus, because there's always a constant reaction with water.
Right. That water dissociation, the water reacting with another water, produces some hydronium. So there are actually two sources contributing to the concentration of hydronium, but the amount that comes from the dissociation of water is very small. Like if we were writing our answers to maybe like more than 3 sig figs, then it would be impactful. But if we're writing our numbers to 3 sig figs, that hydronium dissociate, or the hydronium formation from the dissociation of water, does not have a large impact on the concentration of hydronium we're looking at to 3 sig figs. So that's the assumption we can make, and that will simplify our maths. If we know the hydronium concentration provided by the weak acid, that's all we need. The second assumption is that in a weak acid, we assume that the concentration of that weak acid at equilibrium is the same as the initial concentration of weak acid at like 0 seconds, when the instant we put it in water. We know that some of that acid does react with water and dissociates, but it's such a small proportion, very small, that we can assume that the concentration at equilibrium is basically still the same as it was initially. So that simplifies our maths a bit too. So we're lazy chemists, we make these assumptions, but they're valid, we've checked them.
I'm assuming at higher levels of chemistry you no longer make those assumptions and you just have really long answers.
Yeah, because you know how some weak acids are kind of fairly strong, right? So when it gets to the point where the weak acid is kind of a strong acid, you can't really make these assumptions as much. So you do need to do, like, solve some quadratic equations eventually, things like that. But not at this level. In high school chemistry, we hate quadratic equations in chemistry. We'll do everything to avoid them. But you can solve quadratic equations. You know how to do that.
I've completely forgotten how. Actually.
Just use the quadratic formula.
Yeah, that thing.
Plus or minus the square root of b squared take away 4ac over 2a.
Why? Do you know that?
There's no y in it.
I wouldn't know. Because it's such a cool formula.
Okay, so these are the two assumptions. Like I said, you will be quizzed on them probably from time to time. They are important to know, and it makes our maths simpler. Look at what I've done. I've applied the first assumption to the equation in the box, which we know. We know this equation on the left quite well. It's the expression I introduced at the beginning of today's lesson. But when we make the assumption and plug in that expression, that the hydronium concentration equals the conjugate base concentration, and we plug one in for the other, our equation gets simplified, right? If we plug in H3O plus for the conjugate base, then we have H3O plus times H3O plus, which we can simplify to H3O plus squared. So we have one number in the numerator, we're plugging in and squaring it. That's cool. I like simpler maths. And we're still dividing it by the acid concentration, but once again, how does that link with our second assumption? We are plugging in the concentration of acid at time 0 before this reaction started, because we can assume that very little of it actually dissociated over the course of the reaction as it established equilibrium. I want to go over one example of the maths because it's pretty simple. Now that we've finally gotten to this equation today, and all I've been doing is trying to explain how I've gotten to this equation today, we can apply it and solve for various quantities in the expression. We could use it to calculate the weak acid constant for an acid. We could use it to calculate the concentration of an acid if we know everything else, right? So if I told you a weak acid had a Ka value of such and such, and I told you the pH of the acid, you would know the hydronium concentration. You know the Ka. You could find the concentration of the acid. You could solve for Ha, right? So we're always going to have one unknown, one thing we don't know in this expression, and we should know everything else. So let's apply it. Let's work through this problem here. So this was from the 2015 exam. It was a merit level question. We need to find the pH. Let's work through it on the board before we reveal the answer. The first two things we should always do, even if you don't know what to do, is write what?
Chaos expression.
In this case, we're going to write the Ka expression. But that's the second thing we'll do. So the first thing of the two things we should always do is write the balanced chemical equation first. So actually, there's kind of two equations going on. I want to make you aware of the two equations going on. And I'm going to break my own rule first. I'm using a forward arrow. And this is actually what's happening. This is an ionic compound, right? I know it's ionic because it contains chloride. Chloride is an ion. So what first happens is when you put this in water, it's like table salt. It dissolves. It dissociates completely. I'm talking about the ionic compound dissociating completely. So it's going to break apart to form a cation and an anion, obviously. So CH3, NH3 plus, and we're forming a chloride ion as well. Now, after it's dissociated, and this is a physical change, it's not a chemical reaction, it's just physically breaking apart. Now a chemical reaction will occur, and that's between this. This is the weak acid, which will react with water. So now I can write my equilibrium equation showing the weak acid ion reacting with water in equilibrium. And because it's a weak acid, it is donating. So now I've got my conjugate base formula, and I've formed hydronium. And let's put states of matter on things, right? So everything's usually aqueous unless we're looking at water. Cool. Now I've got this equation, I can write a Ka expression for it. So products over reactants, square brackets for concentration. You don't need states of matter in this expression, you can just write the species. Cool, there we go. I've written the expression, but let's simplify it a bit. Remember one of those assumptions we just looked at, right? So I can assume that these two species concentrations are equal up here, so it simplifies to the square of the hydronium concentration. I do hear the music now, Ella. There we go. And so we want to calculate the pH. So which of these three things in this form of the equation right now are we actually solving for? Are we solving for Ka? No.
Concentration of hydronium.
Right, because we can convert hydronium concentration to pH in the end. You know how to do that from level 2. That's easy, right? But we know Ka. It's given to us in the question. It has to be. And we know the concentration of, well, we know the concentration of the ionic compound, but it's dissociated in a 1-to-1 ratio. So that allows us to know right away the concentration of this species, right? It's the same. And because even though some of it dissociates, so the concentration isn't quite 0.0152 anymore, we can assume that so little actually did dissociate that at equilibrium it's still pretty much the same concentration. So we can plug that number in down here. Cool. So when we do that, we follow these same steps we talked about. You're going to have to rearrange this equation, and to get rid of the square, you're going to have to take the square root, right? So you're going to have to take the square root of Ka